In this exercise 102A, we analyze a rectangular plate with a central hole similar to the one used in previous exercises, with the same dimensions of 100 millimeters by 40 millimeters and 3 millimeters thickness. The plate is made of 2024 T3 aluminum and is subjected to a tensile load of 40 kilonewtons. The aim is to carry out a 2D finite element analysis to evaluate both the gross and net stress concentration factors caused by the presence of the 10 millimeters diameter hole. The solution follows the standard FE analysis process, from geometry modeling to post-processing. Steps like defining material properties, selecting element types, and applying boundary conditions can be referred from earlier exercises as they remain unchanged. The key focus here is on solving the model and interpreting the results to understand how the hole influences stress distribution under tensile loading. In step 1 of the analysis, we begin by creating the geometry of the plate using FreeCAD. To prepare the model for finite element analysis, the geometry is split into multiple surface regions around the hole. This helps in achieving better mesh control and improved stress resolution in critical areas. While there are many ways to perform surface splitting, such as using Boolean operations, face partitions, or sketch-based subdivisions, in this case, we have chosen a simple sketch-based method with construction lines and angled cuts to divide the geometry. This method ensures symmetry and mesh uniformity, which are crucial for accurate FE results. The model tree confirms the creation of multiple surfaces, which we will later use for meshing. After completing the surface splitting in FreeCAD, the geometry is exported, typically as a step file, and then imported into Prepomax for mesh generation and FE setup. Once the model is loaded in Prepomax, each of the individual surfaces appears as a separate shell part. To ensure proper mesh continuity and analysis behavior, all the shell parts need to be combined into a single compound part. This can be done in two ways: by right-clicking on the selected parts in the geometry tree and choosing Create Compound Part from the context menu, or by going to the Geometry tab at the top menu and selecting the same function from there. In the image, each surface is still shown as an individual part, highlighted in different colors. Once the compound is created as shown in the bottom image, the geometry is unified into one consistent model. This is a critical step before meshing, as it ensures that all surfaces are properly connected and that the solver treats the structure as a single, continuous body during the FE analysis. In step 2, Mesh, we define the mesh setup for the compound geometry within Prepomax. The meshing is done using the shell gmesh algorithm, which is suitable for 2D shell-type models like this plate with a central hole. We begin by setting up the meshing parameters, where we control mesh size and refinement. In this case, the maximum element size is set to 3 millimeters, and the minimum element size is 0.2 millimeters, allowing finer resolution near the hole and maintaining a reasonable element count elsewhere. Additionally, element size per edge is specified to be 2 millimeters, which helps maintain consistency across surfaces. Then, under the shell gmesh settings, we choose a quasi-structured quad mesh, which helps maintain a more uniform and accurate element layout, particularly beneficial for stress concentration zones like the area around the hole. After defining the meshing parameters and shell settings, the next step is to generate the mesh. This is done in Prepomax by going to the top menu bar and selecting Mesh, then Create Mesh, or simply right-click on the modal and select Create Mesh. Before doing this, make sure the compound geometry created earlier is selected. This ensures that the mesh is applied to the unified model rather than to individual surfaces. In the Parts Selection window, choose Compound 1 from the list of available parts, then click Continue to proceed. Once the mesh is created, it appears in the model view as shown in the lower image. The result is a well-structured mesh with refinement around the circular hole and a clean quadrilateral layout across the entire plate. This mesh layout is especially effective for accurately capturing stress gradients around the discontinuity, which is critical when evaluating stress concentration factors in later analysis steps. At this stage, the mesh has already been generated, and we proceed directly to step 5, run the analysis. The intermediate steps, such as material definition, section assignment, boundary conditions, and loading setup, are not explained here, as these have already been covered in detail in the earlier exercises. As shown, a reference point is defined on the right edge of the plate, where the tensile force is applied, while the left edge is fully fixed to simulate boundary constraints. To start the analysis, right-click on the analysis step and select Run. Once the job finishes successfully, as confirmed in the output window, we can move forward to the post-processing stage by clicking the Results button. This allows us to view stress distributions and extract necessary data for evaluating stress concentration factors. In this step, we visualize and interpret the results after the analysis is successfully completed. By switching to the Results tab in Prepomax, we can access various field outputs such as displacements and stresses. For this exercise, we focus on von Mises stress under the stress output category. The stress plot shows a clear concentration around the edge of the hole, as expected. The maximum von Mises stress is observed near the hole boundary with a value of approximately 1043 megapascals. This localized peak helps us determine the stress concentration factor, KT, by comparing it with the nominal stress at the gross cross-section or the net section. The lower image provides a zoomed-in view around the hole, clearly highlighting the stress contours and enabling precise evaluation of the critical region. This step completes the FE analysis, and the results can now be used to compute gross and net stress concentration factors for final assessment. In this final part of Step 6, we move on to validation of the FE results by comparing them with analytical data from different references. The gross stress based on the total cross-sectional area is calculated as 333 megapascals, while the net stress, which accounts for the reduced area due to the hole, is 444 megapascals. From the FE analysis, the maximum stress near the hole is obtained as 1043 megapascals. Using these values, the gross stress concentration factor is calculated as 3.13 and the net stress concentration factor as 2.35. When we compare these with Peterson's reference, we find a gross stress concentration factor of 3.19 and a net factor of 2.4, leading to a theoretical maximum net stress of 1,063 megapascals. This validation reinforces confidence in the simulation workflow and highlights the importance of cross-checking numerical results with established empirical references. This set of images illustrates the effect of using different mesh densities and element arrangements around the hole, with the purpose of highlighting how mesh refinement influences the accuracy of the maximum stress values. Each model uses a slightly different configuration in terms of element size and distribution near the hole, which directly affects the peak stress captured in the simulation. As shown, coarser meshes underestimate the stress, while finer meshes provide values that are much closer to the expected maximum. The goal here is to highlight why mesh convergence is important and why we need enough detail in key areas to get accurate results. In the next slide, we will present a graphical comparison of these variations to better visualize how the number of elements around the hole impacts the stress prediction. This graph shows how the gross stress concentration factor changes with the number of elements placed around the perimeter of the hole. As we increase the number of elements, the calculated stress concentration factor becomes more accurate and begins to level off, approaching the reference value from Peterson's chart, represented by the orange line. This confirms that using a finer mesh near the hole leads to results that are closer to the theoretical expectation. It also visually supports the idea from the previous slide that having too few elements can significantly underestimate stress, while a sufficiently refined mesh provides reliable and accurate results.